table, my gambling den. Gold's my bling, mercury be the pen. Eyes and eyebrows got atoms at my whim. Chemical reactions drop beats and swim. Flask in the lab coat, stirring like a potion. Sodium chloride, oceans of ocean. Molecular structures twist and pop up on the grid. Carbon got the diamond shine up this lid. Chemistry chronicles the elements sing. Flipping transformation, science king. Chemical bonds flex electric sing. Molecular magic, chaos we bring. Acids and bases duel like in the street. pH levels tip, balance and feed. Hydrogen's a rocket up to the stars. Electrons pass, trace, outshine cars. Distillate fire, ethanol's play. Mendeleev's vision rules the day. Iron oxidizes, rust on donuts. Alkaline rise, power in our guts. Reactants meet enzymes, speeding up the show. Energy barriers, let them all go. Catalyst of rhythm, reaction groove. Chemical romance makes molecules move.
An introductory chemistry course typically provides a fundamental understanding of the basic principles and concepts of chemistry. It is designed to introduce students to the study of matter, its properties, and the changes it undergoes. The course usually covers a wide range of topics, including basic concepts, matter, atoms, molecules, elements, compounds, and the periodic table. Atomic structure, protons, neutrons, electrons, isotopes, and electronic configurations. Chemical bonding, ionic, covalent, and metallic bonds. Chemical reactions, types of chemical reactions, stoichiometry, and thermochemistry. States of matter, solids, liquids, and gases, and their properties. Solutions, concentration, solubility, and colligative properties. Acids and bases, definitions, properties, and reactions. Redox reactions, oxidation and reduction, and balancing redox equations. Organic chemistry, introduction to hydrocarbons and functional groups. The course may also include laboratory experiments to provide students with hands-on experience in applying the concepts learned in the lectures. Introductory chemistry courses are typically taken by students who are interested in pursuing a degree in chemistry, or who need a basic understanding of chemistry for other science or engineering disciplines. 1. Matter and its properties. States of matter, solid, liquid, gas, and plasma, understanding their characteristics and transitions between them: melting, freezing, boiling, condensation, sublimation, deposition. Classification of matter, pure substances, elements and compounds versus mixtures, homogeneous and heterogeneous. Physical and chemical properties, distinguishing between properties that can be observed without changing the substance's composition, color, density, melting point, and those that involve a change in composition, flammability, reactivity. 2. Atomic structure. Subatomic particles, protons, neutrons, and electrons, their location, charge, and relative mass. Atomic number and mass number, defining elements based on the number of protons and understanding isotopes, atoms of the same element with different numbers of neutrons. Electron configuration, how electrons are arranged in energy levels and sublevels within an atom, and how this relates to an element's chemical properties. Periodic table, organization of elements based on their properties and electron configurations, trends in the periodic table: electronegativity, ionization energy, atomic radius. 3. Bonding and interactions. Ionic bonding, transfer of electrons between atoms to form ions, and the electrostatic attraction between those ions. Covalent bonding, sharing of electrons between atoms to form molecules. Polarity, understanding how unequal sharing of electrons can lead to polar covalent bonds and molecules with dipole moments. Metallic bonding, the sea of electrons model and how it explains the properties of metals' conductivity, malleability, ductility. Intermolecular forces, forces of attraction between molecules, hydrogen bonding, dipole-dipole interactions, London dispersion forces and their influence on physical properties. 4 chemical reactions. Chemical equations, representing chemical reactions using symbols and formulas, balancing equations to satisfy the law of conservation of mass. Types of reactions, common reaction types: combination, decomposition, single displacement, double displacement, combustion. Stoichiometry, quantitative relationships between reactants and products in a chemical reaction, mole concept, molar mass, limiting reactants, percent yield. Reaction rates, factors affecting the speed of a reaction: temperature, concentration, surface area, catalysts. Equilibrium, reversible reactions and the concept of dynamic equilibrium. 5 acids, bases, and solutions. Definitions of acids and bases, Arrhenius, Bronsted-Lowry, and Lewis definitions. pH scale, measuring acidity and basicity. Acid-base reactions, neutralization reactions and the formation of salts. Solutions, solute, solvent, concentration units: molarity, molality, percent composition. Solubility, factors affecting the solubility of substances. 6 Thermochemistry. Heat and energy, understanding heat transfer, exothermic and endothermic processes. Enthalpy, heat content of a system. Calorimetry, measuring heat changes in chemical reactions. 7 Other important topics. Oxidation reduction reactions, transfer of electrons between species, oxidation numbers, balancing redox equations. Gases, gas laws: Boyle's law, Charles's law, Avogadro's law, ideal gas law, kinetic molecular theory. Nuclear chemistry, radioactivity, nuclear decay, half-life. This list provides a more comprehensive overview of the core ideas typically covered in an introductory chemistry course. Remember that the specific topics and depth of coverage may vary depending on the curriculum and level of the course. Course syllabus: Introductory Chemistry. Course description: this course provides a fundamental introduction to the principles and concepts of chemistry. It will explore the nature of matter, its properties, and the changes it undergoes. Through lectures, discussions, and laboratory exercises, students will develop a solid foundation in the core areas of chemistry, including atomic structure, chemical bonding, chemical reactions, states of matter, solutions, and acids and bases. Course objectives: upon successful completion of this course, students will be able to describe the fundamental properties of matter and classify matter into different categories. Explain the structure of the atom, including subatomic particles and electron configurations. Understand the principles of chemical bonding, including ionic, covalent, and metallic bonds. Predict the products and balance chemical equations for various types of reactions. Apply stoichiometric principles to calculate quantities in chemical reactions. Explain the behavior of gases, liquids, and solids. Understand the properties of solutions and calculate solution concentrations. Define acids and bases according to different theories and understand their properties. Perform basic laboratory techniques and analyze experimental data. Develop critical thinking and problem-solving skills related to chemical concepts. Course Outline, Unit 1, Introduction to Chemistry. What is chemistry? Scientific method, measurement and units. SI system, matter and its properties. States of matter, classification of matter, physical and chemical changes. Unit 2, Atomic structure, atoms and subatomic particles, isotopes and atomic mass. The periodic table and periodic trends. Electron configurations. Unit 3, Chemical bonding, ionic bonding, covalent bonding, polar and nonpolar Lewis structures, molecular geometry, intermolecular forces. Unit 4, Chemical reactions, writing and balancing chemical equations, types of chemical reactions, stoichiometry, mole ratios, limiting reactants, percent yield, thermochemistry, energy changes in reactions. Unit 5, States of matter, kinetic, molecular theory, gases, gas laws, ideal gas law, liquids and solids, intermolecular forces, phase changes. Unit 6, Solutions, types of solutions, solubility, concentration units, molarity, molality, percent composition, colligative properties. Unit 7, Acids and bases, definitions of acids and bases, Arrhenius, Brønsted-Lowry, Lewis pH scale, acid-base reactions, neutralization buffers. Unit 8, Introduction to Organic Chemistry, hydrocarbons, functional groups. Laboratory experiments, laboratory safety. Measurement and uncertainty. Separation of mixtures. Chemical reactions. Stoichiometry. Solutions. Acids and bases. Assessment, exams, midterm and final, 60%. Laboratory reports, 20%. Grading scale, A, 90 to 100%. B, 80 to 89%. C, 70 to 79%. D, 60 to 69%. F, below 60%. Note, this is a sample syllabus and may be subject to change at the discretion of the instructor. 1. The thalidomide tragedy. Chemical focus. Thalidomide, a drug developed in the 1950s, was initially marketed as a sedative and to alleviate morning sickness in pregnant women. Tragedy. Thalidomide was later found to cause severe birth defects, including phocomelia, abnormally short limbs, in thousands of children worldwide. Chemical explanation. Thalidomide exists as two mirror image forms enantiomers. While one form had the desired sedative effect, the other caused the devastating birth defects. This highlighted the critical importance of understanding molecular chirality handedness in drug development. Impact. The thalidomide tragedy led to significant reforms in drug safety regulations, including stricter testing protocols and a greater emphasis on understanding the potential side effects of medications. 2. The Bhopal gas tragedy. Chemical focus. Union Carbide's pesticide plant in Bhopal, India, leaked methyl isocyanate mic, a highly toxic gas, in 1984. Tragedy. The gas leak resulted in the deaths of thousands of people and caused widespread injuries and long-term health problems for countless others. Chemical explanation. Mic is a highly reactive chemical that can react violently with water, producing toxic byproducts. The leak occurred due to a combination of factors, including equipment failures, inadequate safety procedures, and a lack of proper training. Impact. The Bhopal disaster highlighted the dangers of industrial chemical accidents and the importance of robust safety measures and environmental regulations in the chemical industry. 3. The Flint water crisis. Chemical focus. The city of Flint, Michigan, switched its water source to the Flint River in 2014 to save money. However, the river water was more corrosive and lacked adequate corrosion control treatment. Tragedy. The corrosive water leached lead from aging pipes into the drinking water supply, exposing residents to high levels of lead, a neurotoxin, particularly harmful to children. Chemical explanation: lead is a heavy metal that can cause serious health problems, including developmental delays, learning disabilities, and behavioral problems. Impact: the Flint water crisis exposed serious failures in environmental protection and public health. It also highlighted the importance of access to clean and safe drinking water for all communities. For the Exxon Valdez oil spill. Chemical focus: the 1989 Exxon Valdez oil spill in Alaska released millions of gallons of crude oil into Prince William Sound, causing widespread environmental damage. Tragedy: the oil devastated marine life, including birds, sea otters, and fish. It also impacted coastal ecosystems and had significant economic consequences for the fishing industry. Chemical explanation: crude oil is a complex mixture of hydrocarbons. When released into the environment, it can contaminate water and soil, harming wildlife, and disrupting ecosystems. Impact: the Exxon Valdez spill led to increased regulations on oil tankers, including the development of double-hulled vessels, and spurred the development of oil spill response technologies. 5. The Fukushima Daiichi nuclear disaster. Chemical focus: the 2011 earthquake and tsunami in Japan caused a nuclear meltdown at the Fukushima Daiichi nuclear power plant. Tragedy: the accident released significant amounts of radioactive materials into the environment, including cesium-137 and iodine-131. Chemical explanation: radioactive materials emit harmful radiation that can damage DNA and increase the risk of cancer. The Fukushima disaster highlighted the potential dangers of nuclear power and the importance of robust safety measures to prevent such accidents. Impact: the Fukushima disaster had a significant impact on public perception of nuclear power and led to increased scrutiny of nuclear safety regulations worldwide. 6. Minamata disease, a tragedy of industrial pollution. The core issue: industrial wastewater contaminated with methyl mercury, a highly toxic form of mercury, poisoned the residents of Minamata Bay, Japan. The impact: this led to severe neurological disorders, birth defects, and countless deaths. The science: methyl mercury, a potent neurotoxin, bioaccumulates in the food chain, concentrating in fish and shellfish. The lesson: Minamata serves as a stark reminder of the devastating consequences of industrial pollution and the importance of responsible waste management. 7. Love Canal, a buried secret unleashed. The core issue: a residential neighborhood was built atop a buried toxic waste dump in Love Canal, New York. The impact: residents suffered from a range of health problems, including birth defects and cancer, due to exposure to hazardous chemicals leaching from the landfill. The science: the landfill contained a toxic cocktail of chemicals, including benzene, dioxin, and other carcinogens, which contaminated the soil, groundwater, and air. The lesson: Love Canal became a symbol of environmental injustice and spurred the creation of the Superfund program to clean up hazardous waste sites across the United States. 8. Agent Orange, the lingering shadow of war. The core issue: the widespread use of Agent Orange, a herbicide and defoliant containing the highly toxic dioxin, during the Vietnam War had devastating long-term consequences. The impact: veterans and their families continue to suffer from health problems, including cancer and birth defects, linked to Agent Orange exposure. The science: dioxin is a persistent organic pollutant that bioaccumulates in the environment and can cause severe health effects. The lesson: Agent Orange serves as a grim reminder of the environmental and human costs of chemical warfare and the importance of considering the long-term consequences of our actions. 9. The ozone hole, a warning from the stratosphere. The core issue: the discovery of a gaping hole in the ozone layer over Antarctica in the 1980s shocked the world. The impact: the ozone layer shields Earth from harmful UV radiation. Its depletion increases the risk of skin cancer, cataracts, and damage to ecosystems. The science: chlorofluorocarbon CFCs, once widely used in refrigerants and aerosols, were found to be responsible for ozone depletion. The lesson: the ozone hole crisis led to the Montreal Protocol, an international agreement that successfully phased out ozone-depleting substances, demonstrating the power of global cooperation to address environmental challenges. 10. Climate change, a planetary fever. The core issue: the Earth is running a fever. Human activities, primarily the burning of fossil fuels, are releasing excessive amounts of greenhouse gases into the atmosphere. The impact: this greenhouse effect traps heat, causing a cascade of disruptions, rising sea levels, more frequent and intense extreme weather events like droughts, floods, and wildfires, and the disruption of delicate ecosystems. The science: greenhouse gases like carbon dioxide and methane act like a blanket, trapping heat that would otherwise escape into space. This imbalance is causing the planet to warm at an alarming rate. The lesson: climate change is a global emergency demanding urgent action. Transitioning to renewable energy sources, improving energy efficiency, and embracing sustainable practices are crucial for mitigating the worst impacts and ensuring a habitable planet for future generations. Key considerations for Week 1 based on case studies. Thorough onboarding: safety first. If working in a lab or with hazardous materials, prioritize understanding safety protocols. This is crucial, as seen in cases like the Bhopal gas tragedy and the Love Canal disaster. Compliance: be aware of and adhere to all company policies and regulations. The Volkswagen emissions scandal serves as a stark reminder of the consequences of non-compliance. Data integrity: if handling data, understand data security protocols and the importance of accuracy and transparency. The Theranos case highlights the dangers of manipulating or misrepresenting data. Open communication and questioning: speak up if you notice any safety concerns, ethical dilemmas, or potential issues. Don't hesitate to speak up to your supervisor or a designated contact. The Bhopal gas tragedy emphasizes the importance of reporting concerns promptly. Ask questions: don't be afraid to ask clarifying questions to ensure you understand your tasks and responsibilities. The thalidomide tragedy underscores the importance of thorough understanding and communication in the pharmaceutical industry. Seek guidance: if you encounter challenges, seek guidance from experienced colleagues or mentors. Ethical considerations: prioritize safety and integrity. Always prioritize safety and integrity in your work, even if it means facing challenges or delays. The Ford Pinto case serves as a cautionary tale about the dangers of prioritizing profit over safety. Environmental awareness: be mindful of the environmental impact of your work. The Exxon Valdez oil spill and the climate crisis highlight the importance of environmental responsibility. Data privacy and security: respect the confidentiality and privacy of any data you handle. The Theranos case emphasizes the importance of data security and ethical data handling practices. 11. J.J. Thomson and the dawn of subatomic particles. The core issue: scientists once believed atoms were indivisible. The breakthrough: J.J. Thomson's experiments with cathode rays demonstrated the existence of the electron, a negatively charged subatomic particle. 1. Unit 2 connection: this discovery shattered the notion of the atom as the smallest unit of matter, laying the groundwork for our understanding of protons, neutrons, and the complex inner workings of the atom. 12. Rutherford's nuclear revolution. The core issue: the plum pudding model, picturing a diffuse positive charge with embedded electrons, was the prevailing atomic model. 2. The breakthrough, Rutherford's gold foil experiment, where alpha particles were fired at a thin gold sheet, revealed a small, dense, positively charged nucleus at the center of the atom. 3. Unit 2 connection. This groundbreaking experiment overturned the plum pudding model, establishing the modern concept of the nucleus and its crucial role in atomic structure. 4. 13 Isotopes, variations on a theme. The core issue, early atomic theory focused on a single type of atom for each element. 5. The breakthrough, the discovery of isotopes, atoms of the same element with different numbers of neutrons, expanded our understanding of atomic diversity. 6. Unit 2 connection. This concept explains variations in atomic mass for elements and introduces the concept of radioactivity, arising from the instability of certain isotopes. 7. 14 Mendeleev's vision, organizing the elements. The core issue, a system was needed to organize the growing number of known elements. The breakthrough, Dmitry Mendeleev developed the periodic table, arranging elements by increasing atomic mass and revealing recurring patterns in their properties. 8. Unit 2 connection. The periodic table provides a framework for understanding electron configurations, predicting trends in atomic size, ionization energy, and other key properties. 9. 15 Bohr's model, quantizing the atom. The core issue, how do electrons behave within the atom? The breakthrough, Niels Bohr proposed a model where electrons orbit the nucleus in specific energy levels, like planets orbiting the Sun. 10. Unit 2 connection. This model, while simplified, introduced the concept of quantized energy levels, a fundamental principle in understanding electron configurations and the emission spectra of elements. 16 Quantum mechanics, the rise of wave-particle duality. The core issue, Bohr's model, while insightful, couldn't fully explain the behavior of electrons in more complex atoms. 1. The breakthrough, the development of quantum mechanics, with key contributions from scientists like Schrödinger and Heisenberg, revolutionized our understanding of the electron. 2. It introduced the concept of wave-particle duality, where electrons exhibit both wave-like and particle-like properties. 3. Unit 2 connection. Quantum mechanics provides the framework for understanding the modern model of the atom, where electrons are described by probability distributions orbitals rather than fixed orbits. 4. 17 Pauli exclusion principle, filling the shells. The core issue, how are electrons distributed among energy levels within an atom? The breakthrough, Wolfgang Pauli formulated the exclusion principle, stating that no two electrons in an atom can have the same set of 4 quantum numbers. 5. Unit 2 connection. This principle dictates how electrons fill orbitals within an atom, determining electron configurations and influencing the chemical properties of elements. 6. 18 Hund's rule, maximizing unpaired electrons. The core issue, how do electrons fill orbitals within a given sublevel, e.g. p, d, f? The breakthrough, Hund's rule states that electrons will singly occupy orbitals within a sublevel before pairing up. 7. Unit 2 connection. This rule explains the observed electron configurations of many elements and has implications for the magnetic properties of atoms. 19 Spectroscopy, seeing the atom's fingerprint. The core issue, how can we experimentally observe the energy levels of electrons within an atom? The breakthrough, the development of spectroscopy, particularly atomic emission and absorption spectroscopy, allows scientists to observe the unique spectral lines emitted or absorbed by atoms. Unit 2 connection. These spectral lines provide experimental evidence for the existence of quantized energy levels and can be used to identify elements and determine their electronic structures. 20 The discovery of the neutron. The core issue, while protons and electrons were known, the existence of a neutral particle within the nucleus remained elusive. The breakthrough, James Chadwick's experiments with alpha particle bombardment led to the discovery of the neutron in 1932.8. Unit 2 Connection. This discovery completed the picture of the nucleus, explaining the existence of isotopes and providing insights into nuclear stability and radioactivity. Key considerations for Week 2 based on atomic structure case studies. Building on foundations. Rutherford's experiment, just as Rutherford built upon existing knowledge to revolutionize atomic theory, build upon your first week's learning. Refine your understanding of basic concepts like subatomic particles and the periodic table. Embrace the unknown. Quantum mechanics, like the shift from classical to quantum mechanics, be prepared to embrace new concepts and adapt to new information. The world of atomic structure is constantly evolving. Maintain a curious and inquisitive mindset. Precision and accuracy. Spectroscopy. Spectroscopy emphasizes the importance of precise measurements and accurate observations. 1. In your work, strive for accuracy and attention to detail in all your tasks. Collaboration and communication. Mendeleev's periodic table. Mendeleev's development of the periodic table involved organizing and synthesizing information from various sources. Collaborate effectively with colleagues, share knowledge, and communicate your findings clearly. Continuous learning. The discovery of the neutron, just as the discovery of the neutron expanded our understanding of the atom, continuously seek to expand your knowledge and skills. Stay curious and explore new concepts and technologies. Ethical considerations. Radioactivity. The discovery of radioactivity highlighted the potential dangers and ethical implications of scientific advancements. Be mindful of the ethical considerations in your work and strive to use your knowledge responsibly. 21. The birth of the ionic bond, understanding electrostatic attraction. Core concept. Ionic bonds arise from the electrostatic attraction between oppositely charged ions formed by the transfer of electrons between atoms. Significance. This concept explains the formation of many stable compounds and their unique properties, such as high melting points and solubility in water. Unit 3 Connection. This case study introduces the fundamental principles of ionic bonding, emphasizing the role of electron transfer and the formation of stable ionic lattices. 22. Covalent bonding. Sharing is caring. Core concept. Covalent bonds form when atoms share pairs of electrons to achieve a stable electron configuration. Significance. Covalent bonding is the foundation for the formation of countless molecules, from simple diatomic molecules like hydrogen H2 to complex biological molecules like DNA. Unit 3 Connection. This case study explores the nature of covalent bonds, including single, double, and triple bonds, and introduces concepts like electronegativity and bond polarity. 23. Metallic bonding, a sea of electrons. Core concept. Metallic bonds arise from the delocalization of valence electrons among a lattice of metal atoms. Significance. This unique bonding mechanism explains the characteristic properties of metals, such as high conductivity, malleability, and ductility. Unit 3 Connection. This case study explores the sea of electrons model and its implications for the physical and chemical properties of metals. 24. V-spare theory. Predicting molecular shapes. Core concept. The valence shell electron pair repulsion. V-spare theory predicts the three-dimensional shapes of molecules based on the repulsion between electron pairs around a central atom. Significance. V-spare theory provides a powerful tool for understanding the geometries of molecules, which significantly influences their physical and chemical properties. Unit 3 Connection. This case study connects the concepts of electron pairs, bond angles, and molecular shapes to the underlying principles of covalent bonding. 25. Intermolecular forces, weak bonds, big impact. Core concept. Intermolecular forces are weak attractive forces between molecules, such as hydrogen bonding, dipole-dipole interactions, and London dispersion forces. Significance: despite their weakness, intermolecular forces play a crucial role in determining the physical properties of substances, such as boiling points, melting points, and solubility. Unit 3 Connection. This case study explores the different types of intermolecular forces and their influence on the macroscopic properties of substances. 26 The discovery of the noble gases, a challenge to the octet rule. Core concept: the discovery of the noble gases helium, neon, argon, etc. challenged the early understanding of chemical bonding, as these elements exist as stable monatomic gases despite having incomplete valence shells. Significance: the discovery of the noble gases led to the refinement of the octet rule and the development of more sophisticated theories of chemical bonding. Unit 3 Connection. This case study explores the exceptions to the octet rule and introduces the concept of expanded octets in certain molecules. 27 Linus Pauling and the nature of the chemical bond. Core concept: Linus Pauling, through his pioneering work on chemical bonding, developed concepts like electronegativity and resonance, which revolutionized our understanding of molecular structure and reactivity. 1. Significance: Pauling's work laid the foundation for modern theories of chemical bonding and earned him the Nobel Prize in Chemistry. 2. Unit 3 Connection. This case study highlights the contributions of a prominent scientist in advancing our understanding of chemical bonding and its implications for various fields of chemistry. 28 Hydrogen bonding, a unique intermolecular force. Core concept: hydrogen bonding is a strong type of dipole-dipole interaction that occurs between a hydrogen atom bonded to a highly electronegative atom such as oxygen, nitrogen, or fluorine 3 and a lone pair of electrons on another electronegative 4 atom. 5. Significance: hydrogen bonding plays a crucial role in many biological processes, such as the structure of DNA and the properties of water. 6. Unit 3 Connection. This case study explores the unique characteristics and importance of hydrogen bonding as a key intermolecular force influencing the properties of various substances. 29 The importance of molecular geometry, enzymes and drug design. Core concept: the three-dimensional shape of a molecule is crucial for its function, particularly in biological systems. 7. Significance: understanding molecular geometry is essential for fields like drug design, where the shape of a drug molecule must precisely match the shape of its target receptor site. 8. Unit 3 Connection. This case study emphasizes the importance of V-spare theory and other concepts related to molecular geometry in understanding the interactions between molecules and their biological activity. 30 Nanomaterials, building from the bottom up. Core concept: nanomaterials are materials with at least one dimension on the nanoscale 1 to 100 nanometers. 9. Significance: the unique properties of nanomaterials, often arising from their size and structure, have led to numerous applications in fields like medicine, electronics, and materials science. 10. Unit 3 Connection. This case study explores how the principles of chemical bonding and intermolecular forces play a crucial role in the design and synthesis of nanomaterials with novel and exciting properties. Week 3. Midterm exam. Instructions: answer all questions to the best of your ability. Show all work for calculations, if applicable. Use clear and concise language in your responses. The essay question should be answered in a well-structured format with an introduction, supporting arguments, and a conclusion. Multiple choice 2 points each. Which scientist is credited with the discovery of the electron? A. Ernest Rutherford. B. J. Thomson. 1. C. Niels Bohr. D. Albert Einstein. What is the fundamental unit of charge? A. The proton. B. The neutron. C. The electron. D. The nucleus. Which type of chemical bond involves the sharing of electrons between atoms? A. Ionic bond. 2. B. Metallic bond. 3. C. Covalent bond. D. Hydrogen bond. What is the strongest type of intermolecular force? A. Dipole forces. B. London dispersion forces. C. Hydrogen bonding. D. Ion dipole forces. What is the purpose of the periodic table? A. To organize elements based on their atomic mass. B. To organize elements based on their properties and electron configurations. C. To predict the physical properties of compounds. D. To classify elements as metals, nonmetals, and metalloids. Which of the following is not a subatomic particle? A proton. B. Neutron. C. Electron. D. Molecule. What is the term for atoms of the same element with different numbers of neutrons? A. Ions. B. Isotopes. C. Allotropes. D. Isomers. Which type of chemical bond is typically found in metals? A. Ionic. B. Covalent. C. Metallic. D. Hydrogen. What is the V-spare theory used to predict the number of electrons in an atom? B. The three-dimensional shape of molecules. C. The strength of chemical bonds. D. The reactivity of elements. What is the significance of the discovery of the neutron? A. It explained the existence of isotopes. B. It proved the existence of the nucleus. C. It led to the development of the periodic table. D. It explained the phenomenon of radioactivity. Short answer 5 points each. Briefly explain the difference between ionic and covalent bonding. Provide an example of each. Describe the key features of the Bohr model of the atom. What are its limitations? Explain the concept of electronegativity and its role in determining bond polarity. Describe the three major types of intermolecular forces. What are the key characteristics of metals and how are these properties explained by metallic bonding? Essay question 20 points. Discuss the historical development of our understanding of atomic structure. Begin with early models of the atom and trace the key discoveries and advancements that led to our current understanding. Include the contributions of key scientists like J.J. Thomson, Ernest Rutherford, Niels Bohr, and the role of quantum mechanics in shaping our modern view of the atom. Answer key: B. J.J. Thomson. C. The electron. C. Covalent bond. C. Hydrogen bonding. B. To organize elements based on their properties and electron configurations. D. Molecule. B. Isotopes. C. Metallic. B. The three-dimensional shape of molecules. It explained the existence of isotopes. 31. Combustion, fueling civilization. Core concept: combustion reactions involve the rapid reaction of a substance with oxygen, typically releasing heat and light. 1. Significance: combustion reactions are fundamental to various aspects of human civilization, including energy production, fossil fuels, transportation, and industrial processes. 2. Unit 3 Connection: this case study explores the characteristics of combustion reactions, including their exothermic nature, the role of oxygen, and the formation of common products like carbon dioxide and water. 32. Photosynthesis, harnessing solar energy. Core concept: photosynthesis is a complex series of redox reactions in which plants convert light energy into chemical energy, producing glucose from carbon dioxide and water. 3. Significance: photosynthesis is essential for life on Earth, providing the basis for the food chain and maintaining the oxygen content of the atmosphere. 4. Unit 3 Connection: this case study explores the key steps involved in photosynthesis, including light-dependent and light-independent reactions, and highlights the importance of energy transformations in biological systems. 33. Respiration, energy release in living organisms. Core concept: cellular respiration is a metabolic process that breaks down glucose and other organic molecules to release energy in the form of ATP. 5. Significance: cellular respiration is essential for all living organisms to obtain energy for cellular functions. 6. Unit 3 Connection. This case study explores the various stages of cellular respiration, including glycolysis, the Krebs cycle, and oxidative phosphorylation, and emphasizes the importance of energy transfer in biological systems. Point 7. 34 Stoichiometry in action, the Haber-Bosch process. Core concept: the Haber-Bosch process is an industrial method for synthesizing ammonia from nitrogen and hydrogen. Point 8. Significance: this process revolutionized agriculture by enabling the production of synthetic fertilizers, significantly increasing food production worldwide. Point 9. Unit 3 Connection. This case study highlights the importance of stoichiometric calculations in industrial processes, demonstrating how precise control of reactant ratios is crucial for maximizing product yield and efficiency. 35 Thermochemistry in everyday life, from heating homes to cooking. Core concept: thermochemistry deals with the heat changes that accompany chemical reactions. Point 10. Significance: thermochemical principles are applied in numerous everyday situations, including cooking, heating homes, and operating various industrial processes. Point 11. Unit 3 Connection. This case study explores the concepts of exothermic and endothermic reactions, enthalpy changes, and the practical applications of thermochemistry in everyday life. 36 Acid-base reactions, neutralization and beyond. Core concept: acid-base reactions involve the transfer of protons H+ between species. Point 1. Significance: these reactions are fundamental in many biological and industrial processes, including digestion, environmental remediation, and the production of pharmaceuticals. Unit 3 Connection. This case study explores different acid-base theories: Arrhenius, Brønsted-Lowry, neutralization reactions, and the concept of pH. 37 Redox reactions, electron transfer in action. Core concept: redox reactions involve the transfer of electrons between species. Point 2. Oxidation is the loss of electrons, while reduction is the gain of electrons. Point 3. Significance: redox reactions are essential for many biological processes, such as cellular respiration and photosynthesis, as well as industrial processes like corrosion and electrochemistry. Point 4. Unit 3 Connection. This case study explores the concepts of oxidation and reduction, oxidation numbers, and the balancing of redox equations. 38 Electrochemistry, harnessing redox reactions. Core concept: electrochemistry deals with the interconversion of chemical energy and electrical energy. Point 5. Significance: electrochemical processes are used in various applications, including batteries, fuel cells, and electroplating. Unit 3 Connection. This case study explores the principles of electrochemical cells, galvanic and electrolytic cells, including the role of oxidation-reduction reactions in generating electrical energy. 39 Catalysis, speeding up reactions. Core concept: catalysts are substances that increase the rate of a chemical reaction without being consumed in the process. Point 6. Significance: catalysts play crucial roles in many industrial processes, biological systems, and environmental processes. Point 7. Unit 3 Connection. This case study explores the mechanisms of catalysis, including enzyme catalysis, and its importance in various chemical reactions. 40 Chemical equilibrium, dynamic balance. Core concept: chemical equilibrium is a dynamic state in which the rates of the forward and reverse reactions are equal. Point 8. Significance: understanding chemical equilibrium is crucial for predicting the extent of chemical reactions and controlling reaction outcomes in various industrial and biological processes. Point 9. Unit 3 Connection. This case study explores the principles of chemical equilibrium, including Le-Chatelier's principle, and its applications in various chemical systems. Key considerations for Week 4 based on chemical reactions case studies. Predicting outcomes: combustion and photosynthesis. Just as scientists predict the products of combustion or the outcomes of photosynthesis, learn to anticipate the outcomes of your own work. Optimizing processes. Haber-Bosch process. The Haber-Bosch process exemplifies the importance of optimizing processes for efficiency and yield. Analyze your own work for areas of improvement and seek ways to optimize your workflow. Energy considerations. Thermochemistry and respiration. Understand the energy implications of your work, whether it's managing energy consumption or harnessing energy efficiently. The concepts of exothermic and endothermic reactions are relevant in many fields. Point 1. Equilibrium and dynamic balance. Chemical equilibrium. Recognize that many situations involve a dynamic balance, like chemical equilibrium. Point 2. Be adaptable and able to adjust your approach as circumstances change. Catalysis for improvement. Catalysis. Seek ways to improve your own efficiency and effectiveness, much like catalysts accelerate chemical reactions. Identify areas where you can streamline your work, remove obstacles, or leverage resources more effectively. Ethical implications. Redox reactions and electrochemistry. Consider the ethical implications of your work, particularly in areas like environmental impact, resource consumption, and the development of new technologies. Interdisciplinary approach. Acid-base reactions. Recognize the interconnectedness of different areas of chemistry. Acid-base reactions, for example, have implications for many other areas of study. Approach your work with an interdisciplinary mindset. 41. Water, the universal solvent. Core concept: water's unique properties, such as its polarity and ability to form hydrogen bonds, make it an excellent solvent for many substances. Point 1. Significance: water's solvent properties are crucial for life on Earth, enabling the transport of nutrients and the occurrence of biochemical reactions within living organisms. Point 2. Unit 3. Connection. This case study explores the relationship between the molecular structure of water and its unique solvent properties, including its ability to dissolve polar and ionic compounds. Point 3. 42. Ice, a less dense solid. Core concept: unlike most substances, water expands when it freezes, resulting in ice being less dense than liquid water. Point 4. Significance: this anomalous property of water has profound implications for aquatic life, preventing bodies of water from freezing solid in winter and allowing for the survival of aquatic organisms. Point 5. Unit 3. Connection. This case study explores the unique structure of ice and its relationship to the hydrogen bonding interactions between water molecules. 43. Atmospheric pressure and weather. Core concept: atmospheric pressure is the force exerted by the weight of the atmosphere. Point 6. Changes in atmospheric pressure drive weather patterns, such as winds and storms. Point 7. Significance: understanding atmospheric pressure is crucial for weather forecasting and predicting extreme weather events. Point 8. Unit 3. Connection. This case study explores the relationship between atmospheric pressure, temperature, and the behavior of gases in the atmosphere. 44. The kinetic molecular theory of gases. Core concept: the kinetic molecular theory describes the behavior of gases in terms of the motion of their constituent particles. Point 9. Significance: this theory provides a microscopic explanation for the macroscopic properties of gases, such as pressure, temperature, and volume. Point 10. Unit 3. Connection. This case study explores the key postulates of the kinetic molecular theory and its application in understanding the behavior of ideal gases. 45. Phase changes and energy transfer. Core concept: phase changes, such as melting, freezing, evaporation, and condensation, involve the absorption or release of energy. Point 11. Significance: Understanding phase changes is crucial for various applications, including refrigeration, air conditioning, and the water cycle. Point 12. Unit 3 Connection. This case study explores the energy changes associated with phase transitions, including the concepts of heat of fusion and heat of vaporization. 46. The solubility of gases in water, the fizz of soda. Core concept: the solubility of gases in liquids, such as carbon dioxide in water, is influenced by factors like temperature and pressure. Significance: this phenomenon explains the effervescence of carbonated beverages and has implications for various natural processes, such as the dissolution of gases in the ocean. Unit 3 Connection. This case study explores the factors that affect gas solubility and their applications in everyday life. 47. Osmosis, the movement of water across membranes. Core concept: osmosis is the net movement of water molecules across a selectively permeable membrane from a region of lower solute concentration to a region of higher solute concentration. Significance: osmosis is a fundamental process in biology, playing a crucial role in cell function, maintaining homeostasis, and the transport of nutrients in plants and animals. Unit 3 Connection. This case study explores the principles of osmosis and its biological and physiological implications. 48. Colligative properties, freezing point depression and boiling point elevation. Core concept: colligative properties of solutions depend solely on the number of solute particles present, not their identity. Examples include freezing point depression and boiling point elevation. Significance: these properties have numerous applications, including antifreeze in automobiles, de-icing roads, and the purification of water through distillation. Unit 3 Connection. This case study explores the various colligative properties and their underlying principles, emphasizing the role of solute particles in influencing the physical properties of solutions. 49. Aqueous solutions and electrolytes. Core concept: aqueous solutions can be classified as electrolytes or non-electrolytes based on their ability to conduct electricity. Significance: understanding the electrolytic behavior of solutions is crucial in various applications, including batteries, electroplating, and biological processes. Unit 3 Connection. This case study explores the factors that determine the conductivity of aqueous solutions, including the nature of the solute and its dissociation in water. 50. Solubility rules, predicting precipitation reactions. Core concept: solubility rules provide guidelines for predicting whether a compound will be soluble or insoluble in water. Significance: these rules are essential for understanding and predicting precipitation reactions, which have applications in various fields, including environmental chemistry and chemical analysis. Unit 3 Connection. This case study explores the common solubility rules and their application in predicting the formation of precipitates in double displacement reactions. Key considerations for Week 5 based on states of matter case studies. Interconnectivity of concepts. Water, the universal solvent, recognize the interconnectedness of concepts. Water's unique properties as a solvent stem from its molecular structure and the presence of hydrogen bonds. Predicting behavior. Atmospheric pressure and weather. Just as changes in atmospheric pressure influence weather patterns, learn to predict and anticipate the outcomes of changes in conditions within your own work or projects. Microscopic versus macroscopic kinetic molecular theory. Understand the connection between microscopic behavior, molecular motion, and macroscopic properties, pressure, temperature. Energy transformations. Phase changes. Recognize that phase changes involve significant energy transformations. Consider the energy implications of your own actions and how to optimize energy use. Biological relevance. Osmosis. Appreciate the significance of these concepts in biological systems. Osmosis, for example, is fundamental to life processes. Practical applications. Colligative properties. Understand the practical applications of these concepts in everyday life and industry, such as the use of antifreeze and the purification of water. Predicting outcomes. Solubility rules. Learn to predict the outcomes of specific situations based on your understanding of underlying principles. Solubility rules allow you to predict the formation of precipitates in chemical reactions. 51. Arrhenius acids and bases, a classical definition. Core concept. The Arrhenius theory defines acids as substances that produce hydrogen ions H+ in water, and bases as substances that produce hydroxide ions O1 in water. 2. Significance. This theory provides a foundational understanding of acid-base reactions and their properties. Unit 3 Connection. This case study explores the limitations of the Arrhenius definition and its applications in understanding common acid-base reactions. 52. Bronsted-Lowry acids and bases, proton transfer. Core concept. The Bronsted-Lowry theory defines acids as proton donors and bases as proton acceptors. 3. Significance. This broader definition expands the concept of acids and bases beyond aqueous solutions, allowing for a more comprehensive understanding of acid-base reactions. 4. Unit 3 Connection. This case study explores the concept of conjugate acid-base pairs and applies the Bronsted-Lowry theory to various chemical reactions. 53. Lewis acids and bases, electron pair donors and acceptors. Core concept. The Lewis theory defines acids as electron pair acceptors and bases as electron pair donors. 5. Significance. This broader definition encompasses a wider range of chemical reactions, including those that do not involve proton transfer. 6. Unit 3 Connection. This case study explores the Lewis definition of acids and bases and its applications in understanding various chemical reactions, including those involving metal ions and complex ions. 54. The pH scale, measuring acidity and basicity. Core concept. The pH scale is a logarithmic scale used to measure the acidity or basicity of a solution. 7. Significance. The pH scale provides a convenient way to quantify the concentration of hydrogen ions in a solution and has numerous applications in various fields, including environmental monitoring, industrial processes, and biological systems. 8. Unit 3 Connection. This case study explores the relationship between pH, hydrogen ion concentration, and the properties of acidic and basic solutions. 55. Buffers, maintaining a constant pH. Core concept. Buffers are solutions that resist changes in pH upon the addition of small amounts of acid or base. 9. Significance. Buffers play a crucial role in maintaining the pH of biological systems, such as blood, and are essential for many industrial processes. 10. Unit 3 Connection. This case study explores the mechanisms of buffer action, the importance of buffer systems in biological and environmental systems, and the factors that influence buffer capacity. 56. Acid rain, environmental impact of air pollution. Core concept. Acid rain forms when emissions of sulfur dioxide and nitrogen oxides react with water vapor in the atmosphere to produce acidic compounds. 1. Significance. Acid rain has significant environmental impacts, including damage to forests, lakes, and aquatic ecosystems. 2. Unit 3 Connection. This case study explores the chemical reactions involved in acid rain formation and its environmental consequences. 57. Antacids, neutralizing stomach acid. 3. Core concept. Antacids are substances that neutralize excess stomach acid, providing relief from heartburn and indigestion. 4. Significance. Antacids are widely used over-the-counter medications for treating acid reflux and other gastrointestinal disorders. 5. Unit 3 Connection. This case study explores the chemical reactions involved in the neutralization of stomach acid by antacids, such as calcium carbonate and magnesium hydroxide. 58 Titrations, quantitative analysis of acids and bases. Core concept: titration is a laboratory technique used to determine the concentration of an unknown acid or base solution. 6. Significance: titrations have numerous applications in analytical chemistry, including the determination of the acidity of soil, the analysis of food and beverages, and the quality control of pharmaceuticals. 7. Unit 3 Connection: this case study explores the principles of acid-base titrations, including the use of indicators to determine the endpoint of the reaction. 59 Acid-base indicators, visualizing pH changes. Core concept: acid-base indicators are substances that change color in response to changes in pH. 8. Significance: indicators are used in titrations and other laboratory procedures to visually monitor pH changes. 9. Unit 3 Connection: this case study explores the mechanisms of acid-base indicators and their applications in various chemical analyses. 60 Buffer systems in blood, maintaining homeostasis. Core concept: the human body utilizes buffer systems, such as the bicarbonate buffer system, to maintain a constant pH in blood. 10. Significance: maintaining a stable blood pH is crucial for the proper functioning of various physiological processes. 11. Unit 3 Connection: this case study explores the role of buffer systems in maintaining homeostasis and their importance in biological systems. Week 6. Final case studies. 61. Rusting, a redox reaction in action. Core concept: rusting of iron is a classic example of a redox reaction, where iron is oxidized to iron 3 oxide in the presence of oxygen and water. Significance: understanding redox reactions like rusting is crucial for preventing corrosion and protecting metal structures. Unit 3 Connection: this case study explores the chemical reactions involved in rusting and the methods used to prevent corrosion, such as galvanization and the use of protective coatings. 62 Batteries, powering everyday life. Core concept: batteries utilize redox reactions to generate electrical energy. In a battery, oxidation and reduction reactions occur at separate electrodes, creating a flow of electrons. Significance: batteries are essential for powering a wide range of devices, from portable electronics to electric vehicles. Unit 3 Connection: this case study explores the principles of electrochemical cells and how redox reactions are harnessed to produce electrical energy in batteries. 63 Photosynthesis and respiration, complementary redox processes. Core concept: photosynthesis and cellular respiration are complementary redox processes. Photosynthesis involves the oxidation of water and the reduction of carbon dioxide, while cellular respiration involves the oxidation of glucose and the reduction of oxygen. Significance: these interconnected redox processes are fundamental for the flow of energy in living organisms and the maintenance of the Earth's atmosphere. Unit 3 Connection: this case study emphasizes the importance of redox reactions in biological systems and their crucial role in the energy cycle of life. 64 Alkenes, the backbone of organic chemistry. Core concept: alkenes are hydrocarbons that contain only single bonds between carbon atoms. They form the basis for a wide range of organic compounds. Significance: alkenes are the primary components of petroleum and natural gas, serving as important sources of energy and raw materials for the chemical industry. Unit 3 Connection: this case study introduces the concept of hydrocarbons, focusing on the structure and properties of alkenes, including methane, ethane, and propane. 65 Isomers, molecules with the same formula, different structures. Core concept: isomers are molecules that have the same molecular formula but different arrangements of atoms. Significance: isomerism plays a crucial role in determining the physical and chemical properties of organic compounds, and has significant implications for the field of medicine and drug design. Unit 3 Connection: this case study explores different types of isomerism, such as structural isomerism and stereoisomerism, and their impact on the properties of organic molecules. 66 Alkenes and alkynes, unsaturated hydrocarbons. Core concept: alkenes contain a carbon-carbon double bond, while alkynes contain a carbon-carbon triple bond. Significance: these unsaturated hydrocarbons exhibit greater reactivity than alkenes and are important building blocks for many industrial chemicals and polymers. Unit 3 Connection: this case study explores the structure and properties of alkenes and alkynes, including their nomenclature and characteristic reactions, e.g. addition reactions. 67 Aromatic compounds, the unique case of benzene. Core concept: aromatic compounds, such as benzene, exhibit unique stability and reactivity due to their delocalized electron systems. Significance: aromatic compounds are widely found in nature and have numerous applications in pharmaceuticals, dyes, and other industries. Unit 3 Connection: this case study explores the structure and properties of benzene and other aromatic compounds, including their characteristic reactions and their role in organic chemistry. 68 Functional groups, the chemistry of life. Core concept: functional groups are specific groups of atoms within a molecule that confer characteristic chemical and physical properties. Significance: functional groups are the building blocks of organic molecules and play a crucial role in determining their reactivity and biological function. Unit 3 Connection: this case study explores the properties and reactivity of common functional groups, such as alcohols, aldehydes, ketones, carboxylic acids, and amines. 69 Polymers, building giant molecules. Core concept: polymers are large molecules formed by the joining of many smaller repeating units called monomers. Significance: polymers have revolutionized modern life, with applications ranging from plastics and synthetic fibers to biomedical materials. Unit 3 Connection: this case study explores the different types of polymerization reactions, addition and condensation, and the properties and applications of various polymers, such as polyethylene, nylon, and DNA. 70 Biomolecules, the molecules of life. Core concept: biomolecules are the organic molecules that make up living organisms, including carbohydrates, lipids, proteins, and nucleic acids. Significance: understanding the structure and function of biomolecules is essential for understanding the chemistry of life and for developing new drugs and therapies. Unit 3 Connection: this case study explores the structure, properties, and functions of key biomolecules, highlighting the importance of organic chemistry in understanding biological processes. 71 The importance of chirality, thalidomide tragedy revisited. Core concept: chirality refers to the handedness of molecules, where two molecules with the same chemical formula have mirror image structures. Enantiomers. Significance: enantiomers can have drastically different biological activities. The thalidomide tragedy highlighted the critical importance of understanding chirality in drug development and the potential consequences of using racemic mixtures of both enantiomers. Unit 3 Connection: this case study emphasizes the importance of considering molecular geometry and stereochemistry in understanding the properties and biological activity of molecules. 72 Protein folding, from sequence to structure. Core concept: protein function is intimately linked to its three-dimensional structure. The process of protein folding involves the spontaneous folding of a polypeptide chain into a specific, Functional conformation. Significance: misfolding of proteins can have serious consequences, leading to diseases such as Alzheimer's and Parkinson's. Understanding protein folding is crucial for drug design and the development of new therapies. Unit 3 Connection. This case study explores the factors that influence protein folding, including hydrogen bonding, hydrophobic interactions, and disulfide bridges, and highlights the importance of protein structure for biological function. 73 DNA replication, the central dogma of molecular biology. Core concept: DNA replication is the process by which a cell creates an identical copy of its DNA before cell division. Significance: accurate DNA replication is essential for the transmission of genetic information from one generation to the next. Unit 3 Connection. This case study explores the mechanisms of DNA replication, including the role of enzymes like DNA polymerase and the importance of base pairing in maintaining the integrity of the genetic code. 74. Enzyme kinetics, understanding enzyme activity. Core concept: enzyme kinetics studies the rates of enzyme-catalyzed reactions. Factors such as substrate concentration, enzyme concentration, temperature, and pH can significantly influence enzyme activity. Significance: understanding enzyme kinetics is crucial for developing new drugs, understanding metabolic diseases, and optimizing industrial processes that utilize enzymes. Unit 3 Connection. This case study explores the Michaelis-Menten equation and other models used to describe enzyme kinetics and their implications for drug design and enzyme inhibition. 75. Green chemistry, sustainable solutions. Core concept: green chemistry focuses on the design and development of chemical products and processes that minimize or eliminate the use and generation of hazardous substances. Significance: green chemistry principles are essential for developing sustainable and environmentally friendly technologies to address global challenges such as pollution and resource depletion. Unit 3 Connection. This case study explores the principles of green chemistry, including atom economy, renewable resources, and the design of safer chemicals, and their applications in various fields, such as pharmaceuticals and materials science. Chemistry Final Exam. Instructions: answer all questions to the best of your ability. Show all work for calculations, if applicable. Use clear and concise language in your responses. The essay question should be answered in a well-structured format with an introduction, supporting arguments, and a conclusion. Multiple choice 2 points each. Which scientist is credited with the discovery of the nucleus? A. J. Thomson, B. Ernest Rutherford, C. Niels Bohr, D. Marie Curie. What type of bond involves the sharing of electrons between atoms? A. Ionic bond, B. Metallic bond, C. Covalent bond, D. Hydrogen bond. What is the strongest type of intermolecular force? A. Dipole forces, B. London dispersion forces, C. Hydrogen bonding, D. Ion dipole forces. What is the pH of a neutral solution? A. 0, B. 7, C. 14, D. 1. Which of the following is not a colligative property? A. Freezing point depression, B. Boiling point elevation, C. Vapor pressure lowering, 1, D. Density. What is the process by which plants convert light energy into chemical energy? A. Respiration, B. Photosynthesis, C. Combustion, D. Fermentation. What is the primary function of enzymes in biological systems? A. To store energy, B. To build cell membranes, C. To catalyze chemical reactions, D. To transport molecules across cell membranes. Which biomolecule is the primary source of energy for most living organisms? A. Proteins, B. Lipids, C. Nucleic acids, D. Carbohydrates. What is the monomer unit of proteins? A. Nucleotides, B. Amino acids, C. Fatty acids, D. Glucose. What is the term for molecules that have the same molecular formula but different three-dimensional arrangements of atoms? A. Isotopes, B. Isomers, C. Allotropes, D. Homologues. Short answer 5 points each. Explain the difference between an exothermic and an endothermic reaction. Provide an example of each. Describe the process of DNA replication. Explain the concept of resonance in organic chemistry. Discuss the environmental impact of acid rain. Explain the role of enzymes in biological systems. Essay question 20 points. Discuss the importance of intermolecular forces in determining the physical properties of matter. Provide specific examples of how different types of intermolecular forces influence properties such as melting point, boiling point, and solubility. Answer key: B. Ernest Rutherford. C. Covalent bond. C. Hydrogen bonding. B7. D. Density. B. Photosynthesis. C. To catalyze chemical reactions. D. Carbohydrates. B. Amino acids. B. Isomers. Final experiment, density column. Materials, tall glass or clear jar. Honey. Corn syrup. Dish soap. Water. Vegetable oil. Food coloring optional. Procedure: gather your materials, make sure you have all the necessary liquids and a tall, clear container. Prepare the liquids, if desired, add a few drops of different food coloring to each liquid to make the layers more visible. Slowly pour the liquids, carefully pour the liquids into the glass in the following order: honey most dense, corn syrup, dish soap, water, vegetable oil least dense. Important: pour each liquid slowly and gently down the side of the glass to avoid mixing the layers. Observations: observe what happens to the different liquids. Do they mix? Do they form distinct layers? Why do the liquids form layers? Explanation: this experiment demonstrates the concept of density. Density is the mass of a substance per unit volume. Denser substances sink in less dense substances. The liquids in this experiment have different densities, causing them to form distinct layers based on their relative densities. Safety precautions: always supervise children during this experiment. Avoid spills and keep the area clean. Learning objectives: understand the concept of density. Observe the relationship between density and the arrangement of substances. Develop observational skills and record observations.
Periodic table, my gambling dead. Goals, my blame, Mercury to the pen. Einstein eyebrows got atoms in my blim. Chemical reactions, drop beats and swim. Flask in the lab coat, stirring like a potion. Sodium chloride, oceans devotion. Molecular structures twist and pop lock on the grid. Carbon got the diamond shine up this lead. Chemistry clinicals, the elements say. Flipping transformation, science came. Chemical bonds, flex, electric stain. Molecular magic, chaos we bring. Acids and bases duel like in the street. pH levels dip, balance and feet. Hydrogen's a rocket, up to the stars. Electrons path traced, outshine cars. Distill and fire, ethanol's play. Mendeley's vision rules the day. Iron oxidizes, rust on donuts. Alkaline rise, power in our guts. Reactors meet enzymes, speeding up the show. Energy barriers, let them all go. Catalyst to rhythm, reaction groove. Chemical runs, makes molecules move. Periodic table, my gambling den. Gold's my bling, Mercury be the pen. Einstein eyebrows got atoms at my whim. Chemical reactions drop beats and swim. Flask in the lab coat, stirring like a potion. Sodium chloride, ocean's devotion. Molecular structures twist and pop lock on the grid. Carbon got the diamond shine up this lead. Chemistry chronicles, the elements sing. Flipping transformation, science came. Chemical bonds, flex, electric stain. Molecular magic. tip balance